When graphing exponential decay, you graph it the same way you graph exponential growth. You make an input-output table. Again, if you look at this example here, we're going to use the same example we did in the previous video about the value of $1, or the purchasing power of $1. So our formula is y equals 0.965 raised to the t. So if we plug numbers in, so if I plug 0 in here for our first input value, if we raise it to the 0, well, anything raised to the 0 is 1. If I put a 1 in, 0.965 raised to the first, I would get 0.965. If I raise it to the second and just type that into a calculator, I would get 0.931. So you could keep going all the way up through 10. I'm going to switch gears here a little bit and show you what our graph would look like. So again, to graph exponential decay, just like graphing exponential growth, you make an input-output table. Probably a pretty good decision to use at least 5 points. We're going to see we're going to use 10 here, and I'm going to talk about this graph here in a little bit, why it doesn't look quite right. But again, try to use at least 5 so you can see really how it's changing as the years go on. If you look at this graph, notice this doesn't look quite like exponential decay. It almost looks like it goes up and down and up and down a little bit. These are going to be rounded values, and that's why that occurs. But what you do is you create your input-output table and you plot the points on your graph. Once you plot them, and you should be aware that this is exponential decay because we're taking that growth factor, which is a number between 0 and 1, and we're raising it to an exponent. We're raising it to the number of years. So you should understand that it's exponential decay. So even though your graph doesn't quite look like exponential decay, you know it is, and you can draw a smooth curve through it. Now if we were to extend this graph and make it a lot bigger, we would see how it starts high and drops really quickly, and then it levels out the closer it comes to 0. Now, the graph said, or the directions say, use the graph to estimate the value of $1 in 10 years. So from our graph, you can say years is 10. Where is it hitting your graph? It's hitting it at 0.7, at about 7 cents. So in, I think it would be 1992, the purchasing power of $1 was just was 70 cents. So again, graphing exponential, both growth and decay, you have to make an input-output table, and you should use at least 5 points. Let's compare the two. Here's our generic model, y equals a times b raised to the t. It's growth if your growth factor here is greater than 1. It's decay if it's between 0 and 1. And we had 2 specific formulas. Initial value times our growth rate raised to the time, or initial value times our decay rate raised to the time. And here, as we get through here, is what our graphs look like. Okay? Again, exponential growth starts slow and steady, and then all of a sudden explodes up. Decay drops pretty rapidly, and then it really slows down as it gets closer to 0. Again, that growth rate, if it's greater than 1, it's growth. If it's between 0 and 1, it's decay. But again, the difference between these exponential models and linear models is linear models are a straight line, and these are what exponential graphs look like.